chapter 2 was all about finding derivatives. Lots of different derivative properties or rules, and applying those to different situations. The ones you saw on your gateway were super complicated. The ones on your test should have been a little less complicated, but then you had to do all the algebra simplification. What we're going to see in chapter 3 is actually applications of derivatives. And in this section in particular, we're going to be looking at extrema on an interval. So to start with, we need a definition of what we mean by extrema. So let f be defined on an interval I containing c. F of c is the minimum, so this is one type of extrema, is a minimum of the function on the interval when f of c is the smallest value. Right? F of c is less than or equal to all the other f of x's. And f of c is the maximum on the interval when f of c is greater than or equal to all of the other function values on that interval. The maximum and minimum values on an interval are the extreme values, or the extrema of the function on that interval. Sometimes they are also called the absolute maximum and the absolute minimum, or global maximum and global minimum. They are the tallest or biggest, they are the shortest or smallest on an interval. And they can occur at one of two basically different locations. There's some variation in what I'm about to say, but there's basically two different ways that your minimum or your maximum or your extrema in general can occur. One way that they can occur is they can occur at endpoints, right? Intervals have endpoints. So if my interval started here and stopped here, then this would be my maximum value. It's just an endpoint. It's the highest place in the whole graph, okay? So it can occur at an endpoint. Another possibility is it can occur at these sort of like dips in the graph or peaks in the graph. So these valleys or peaks. So those are the two possible sort of candidates that we have to check for. Endpoints and then these dipping points or these peaking points. And these particular locations right here are very specific. And in fact, you looked at places where you were asked to find these in earlier sections. You were asked to find where horizontal tangent lines existed. Do you remember that phrase? We didn't do a lot with it, but we did a little bit with it. You were asked to find horizontal tangents, and that was actually sort of a precursor to what we're going to be finding here. We are finding horizontal tangents, or places in particular where the derivative is equal to 0. So if the derivative is 0, you have a peak or a valley, or you test the endpoints. And in fact, you need to test both of those values. Theorem 3.1 goes a little further, and it tells us that if you have a continuous closed interval, then you definitely are going to have an absolute maximum and an absolute minimum. Again, they may be on the endpoints, or they may be on peaks and valleys, but they're definitely going to occur. Notice what it doesn't say. It doesn't say what happens if it's not continuous, right? So if the graph has jumps or gaps or asymptotes, then this doesn't necessarily apply. But if it's continuous, then it applies. We also have what are called relative or local extrema. So if there is an open interval containing c on which f of c is a maximum or a minimum value, you can say that f has a relative maximum or a relative minimum at c f of c. So I always like to give the example of when we moved to Ohio. We were working with the youth group, like the middle school and high school. And many of you have stood up next to me enough to know that I'm not a terribly tall person. I'm 5'4". Up to the point when my mom visited us in Ohio, my mom would have told you that I was tall. Isn't that fascinating? But at that point in our family, I was the tallest female in our family. My mom's 5'2", my granny was 5'1", my aunt was 5'3". Everybody was shorter than I was. So in her perspective, I was tall. So we go to Ohio, and she comes to visit us there at some point too, and realizes that every single teenager in the youth group is taller than I am. Every single one. I mean, even the 7th graders. It's crazy. Every single one is taller than I am. Because it's all what you're comparing it to, right? It's a relative term, tall or short. Who are you comparing yourself to? So that's what we're looking at when we talk about relative extrema. So when we look at, for example, if I had a graph that looked something like, oh, I meant to get a different pen, something like this, it could even continue on. I know we're looking at closed intervals, but imagine the whole graph continued on, or at least continued on further. Maybe I won't put the arrows on the end, but I'll at least make it continue on further. This point would be considered a relative minimum value, because if I looked at the nearby values, it is the shortest one there, right? It's the smallest value. But there are definitely points over here that are smaller. Agreed? I mean, the graph is going further down on the right-hand side of the graph. So it's not an absolute extrema. It's not the smallest value on the entire graph, but in sort of a neighborhood, a grouping around it, it is the smallest value nearby. So we call it a relative extrema. And the same thing's true for this location right here. This would be a relative maximum. In a nearby area or neighborhood around it, it is the tallest value, even though over here, I clearly have values that are in fact taller. So if you can continue to think about that word relative as what is it grouped with, what's nearby, that's what we're going to be looking at. Now these locations, however, like here and here, where we do have these peaks and these valleys, yield what are called critical numbers. So if we have a function defined at the variable c, or the location c, if the derivative is 0, right, it has a peak or a valley, or if the derivative is not differentiable at c, still continuous but not differentiable. So in particular, that would be something where you have a sharp turn, right? Okay, so the derivative is not 0 there, the derivative doesn't exist there. So that's the other location. So we're talking about things that have peaks and valleys. That's this description. And this not differentiable business, we're looking at this description. We call those location critical numbers. Now, they don't have to actually be maximums and minimums, but they stand a chance at being maximums and minimums. So let me draw you another example to show you why they don't have to be maximums or minimums, even if they satisfy this criteria. There's a graph that you are familiar with, y equal x cubed. And that graph, if I've drawn it well, that's not drawn well. I know I don't have it on an axis, but it has this flattening off spot in the middle of it. You guys remember that graph? It's actually at the origin if it's exactly y equal x cubed. That flattening off spot actually has a derivative that's equal to 0 at 0. But if you look in the nearby area around it, it is not a maximum and it is not a minimum. So it's a contender because it is a critical point. It has the derivative equal to 0, but it actually fails to be a maximum or minimum. So sometimes they'll achieve maximum or minimum status and sometimes they won't. And we'll talk about how we make that decision in a moment. But just because it's a critical number doesn't mean it has to be a maximum or minimum. It just means that it might be. So relative extrema then occur only at critical numbers in the following conditions. If f has a relative minimum or maximum value at x equals c, so if it is one of these locations, it will be a critical point. And then if we're looking to see whether or not it's going to be based on it being a derivative equal to 0, we look at guidelines for finding extrema. So what we're looking at specifically is we're looking for critical numbers first. Okay, so finding the extrema means first we find the critical numbers. So what are critical numbers? Well, critical numbers mean we find where the derivative is equal to 0 or where it does not exist. We evaluate the critical numbers, like we plug them into the equation. Okay, this is extrema on a closed interval. By the way, I didn't sort of make highlight of that, but it is a closed interval. We evaluate each of the critical numbers, so we plug them into the original equation. So if the derivative is 0 at x equals 7, we take x equals 7, we plug it into the original equation. So we find the corresponding output values. And we find the endpoints. So we need to figure out what is the y value at each of the endpoints, because remember those were contenders as well, not just these critical number locations, but the endpoints. The one that is the smallest y value of all those points you've just tested is your absolute minimum. And the one that is the largest y value of all those that you've tested is your absolute maximum. So So we're going to do some examples now, okay? So in particular, what our starting point is whenever we're looking at these is we're finding derivatives, setting them equal to 0, and solving. That's our first step. Step number 1 here, we're going to talk about finding critical points means doing just that. Find the derivative, set it equal to 0, or does not exist. If it's got a denominator, that's sometimes the case. And we solve it. So we have this equation. And at this point, you're like, whew, I can find the derivative of that, no problem, right? So you've done lots of harder stuff than that before. So what is the derivative of f of x?
3x squared.
Good, 3x squared minus 6x. Okay, so that's what we've done before. Next, we're going to set it equal to 0, and we're going to solve. So now we're reaching back into the algebra things that we've done in the past, right? So as we're looking at this, we potentially might have to factor, depending on what the equation is. This one we do. We might have to do other kinds of things, shifting things around. Anytime we're dealing with a polynomial, which this one is, factoring is a good first step. What do 3x squared and 6x have in common? And 3. Yeah, so 3 and x, so we can factor a 3x out. So that would leave me with x minus 2. So far, so good? Cool. And then we set each part equal to 0. So 3x equals 0. X minus 2 equals 0. And we solve them. So x is 0 on the first one and 2 on the second one, right? Okay, so these are two possible contenders for being maximums or minimums. Now, we're not actually asked to figure out if they are on this problem. We're just asked to find critical numbers. So these are the critical numbers, and we're done with this part of the problem. Okay, it didn't ask us to go any further. But if I wanted to go further, I would be testing to see whether or not those really are peaks or valleys using the next steps in this guidelines here. Okay, but we don't have a closed interval here. We're just asked to find critical numbers. The next one does ask us to go a little further, though. It asks us to actually find the absolute extrema. So we start out the exact same way, right? We're finding critical numbers, setting things equal to 0, or taking derivatives and setting things equal to 0. So what is the derivative of negative x squared plus 3x minus 5?
2x plus 3.
Good, negative 2x plus 3. That's actually linear, so we don't have to do any factoring with this one. So I am just shifting values. I can move the 3 to the left, so I have negative 2x equals negative 3, and x would be 3/2. So far, so good? Okay, critical point found, right? So this is like step 1 here, we're done. We're done with step 1. Step 2 says I need to find the corresponding y value that goes with that critical number. So over here, then I need to find f of 3/2. Okay, so grab a calculator if you wish, do it in your head if you wish, write it down if you wish, doesn't matter to me. But we're trying to find the output for 3/2 when I have negative x squared plus 3x minus 5. I have my decimal form written down. What does yours say? I'll use decimals. What'd you use?
Negative 2.75.
Decimals might be easier to compare our values in case I have other decimals to compare with them. So decimals would be fine. Fractions would be fine here as well. If you had a fraction, what would you get?
Negative 11 over 4.
Yeah, 11 over 4. So negative 11 over 4 is a fraction. Okay, so this is step 2. I evaluated the critical numbers, right? Step 3 says I need to evaluate the endpoints. So my endpoints are always given on these problems. They're negative 2 and 1. So I'm going from x equals negative 2 on the left to x equals 1 on the right. So we're going to test negative 2 and 1. And it's important to recognize, although it is usually the case, the 3/2 that they're giving us, I need to decide whether it's on that interval or not. Is 3/2 on this interval from negative 2 to 1? It actually is not on this one, right? A lot of times they are, but this one actually isn't. So no matter what happens, the 3/2 is not going to be my absolute maximum or my minimum because it's not on the interval I'm looking at. But I don't know that until I actually get to the point where I'm considering the interval, which is now. So we need to test the endpoints, f of negative 2. So put negative 2 in. and I got back negative 15. Does that look right? And I put in the number 1, and I get back negative 3. So if these numbers had all been on the same interval, this negative 2.75 would actually be my maximum, wouldn't it? Yeah, it's actually bigger than the negative 3, but it's not on my interval. So it might be a good thing to write that to the side, that this is not on the interval negative 2, 1. Right? It just isn't, which means I don't get to consider it. I only get to consider these values. The one that gives me the smallest value is my minimum. That's the first one. The one that gives me my largest value is my maximum, and that's my second one. So here's how we write this out. We say that we have a maximum of negative 3 at x equal 1. We have a minimum of negative 15 at x equal negative 2. Okay? There's another way you can write it out. This is probably my preference, just because I think it wording-wise, you know what you're doing if you can write that down for me. The other thing that you can do, and WebAssign will probably allow, depending on its structure of its language, is that they will often say that there's a maximum, and it'll give the ordered pair. So there's a maximum at 1, negative 3, like that. And then there's a minimum at negative 2, negative 15. And that's okay as well, if you write it that way. So that's sort of my other option. Does that make sense? Okay, let's take a look at the next problem. So sometimes our equations aren't polynomials, right? You know that's going to happen sometimes. This is an example of one. We're having the exact same directions, except that we now actually have an interval where, not an interval, but an equation, excuse me, that's rational. There is a location here where I have an asymptote. Where does my asymptote occur?
2.
It occurs at 2. And it's really important to sort of be aware of that, because does my interval include 2? No. If it did, I would not necessarily even be able to go any further. I would not be guaranteed that I have an absolute maximum and absolute minimum, because the graph would not be continuous if it included the x value of 2. But it doesn't. It only includes x values from 3 to 5. So on the 3 to 5 interval, this is a continuous function. Does that make sense to everyone? Okay. So it fits in with the criteria that we had over here, which says that it is continuous. It really is continuous on this closed interval. So I'm able to work with what I have and go forward with the same process. So I'm going to take the derivative of t over t minus 2. Okay, so that's quotient rule, right? So somebody walk me through, what do you get for the derivative when you do that quotient rule?
T minus 2 minus t over t minus 2.
Okay, so t minus 2, and then it would be times 1 if we were thinking through the details, right? The derivative at the top, minus, and then I'd have my numerator, and the derivative of the denominator happens to also be 1.
All over t minus 2.
Mm-hmm. Okay, everybody good so far? If I clean up my numerator, you'll see very quickly that this t and this t are going to cancel, right? Because they're both multiplied by 1. So I have a t minus 2 minus t. So this ends up just giving me negative 2 over t minus 2. And what I want to know is I want to know whether this is either where this is equal to 0 or does not exist. Now, the only way that this is going to equal 0 is if the numerator equals 0, and it doesn't, right? It's a constant, it doesn't equal 0. If I had other variables up there, I would set the numerator equal to 0 and I would solve. So if I'm looking for this piece on this type of an equation, my numerator would equal 0. But here that can't happen, because my numerator is the constant number negative 2. The only way that I get that it does not exist is if the denominator equals 0. Now, the denominator can in fact equal 0 here, and we know exactly where it has the value where it equals 0. It's at 2. We already talked about it, right? So the denominator equals 0 at t equal to 2, but that's not on my interval. Right? What this tells you as you work your way through is that on my interval, there are no critical points. The graph doesn't have any peaks or valleys between 3 and 5. There just aren't any. So I'm kind of at a point where on this list of things to do, I tried to do number 1. I didn't find any, so I don't have to do number 2. So that's good. So we're left doing number 3, which is simply evaluating the 2 endpoints. So we're finding what happens at 3 and what happens at 5. Oops. So we're going to evaluate h of 3 and h of 5. You can probably do that in your head because the equation's pretty simple. 3 over 3 minus 2 would be, that one's 3. And then 5 over 5 minus 2 would be 5/3. All right, so I only have 2 contending points to consider. I need to know which one's the biggest and which one's the smallest. So which of those 2 is largest?
3.
The 3. So this is my maximum, and this would then be my minimum. Okay, you do need to write the answer out. Like, what does that mean? Well, it either means that you write it as this. You have a maximum of 3 at t, sorry, our variable is t. If you put x, I'm not going to freak out, but WebAssign will. It won't let you put in x if you've got a t in the problem, so just be careful on that. At t equal to 3. And we have a minimum of 5/3 at t equal 5. So you can write it like that if you're working on a quiz or potentially on WebAssign, depending on the structure of their language. Or you might write it in ordered pair form. So there's a maximum at 3, 3. And then there's a minimum at 5, 5/3. Any questions on that? Okay, we have one more example, and it looks like we might be done a little early today. I hope you won't hold that against me.
Of course not.
Of course not. All right. Trig functions, they seem to make a play at any point, right? We have them as well. If you think about your trig functions, particularly sine and cosine is what I'm referring to, they have lots of peaks and valleys, right? They have this cyclic nature. So in a very real sense, they often have critical points because they have lots of peaks and valleys for those 2 functions. And in particular, we're looking at the entire rotation from 0 to 2 pi. So yeah, if I'm looking from 0 to 2 pi, a full rotation of my unit circle, my cosine value is going to hit peaks and valleys. So as we look for critical points, we expect that we're going to find some. So we're going to do the same thing we've did before. We're going to find the derivative. So what's the derivative of 3 cosine x? You guys are really good at this now, aren't you? Negative 3 sine of x. And we're going to set this equal to 0. Now, you can do that in your calculator. The negative 3 is irrelevant at the front, right? If I divide both sides by negative 3, I just get sine of x equals 0. Okay, the negative 3 in terms of a graph just changes the peaks and valleys, how high up and down they go, but not where they'd occur along the x-axis. So you have to think about your sine graph. So either you think about your sine graph or you think about your unit circle. So let me just talk through a couple of those and you can kind of decide what one makes the most sense to you. What you can't do in general is to just simply do inverse sine in your calculator. Inverse sine in your calculator will give you one value and there might be more than one because that's the way it works. So you have to be a little bit careful not to overuse your calculator. But thinking about this, I think, from a visual perspective is pretty good. If you remember what your sine graph looks like, so we'll look at that one first. It actually has this shape between 0 and 2 pi. Okay? If we were looking at cosine, it's shifted. It doesn't look like this between 0 and 2 pi. But this is my graph of sine. Let me label it. This is sine x. So what I want to know is I want to know where that graph has x-intercepts. Because x-intercepts are places where the graph is equal to 0, right? And you see 3 of them. Yeah? 2 of them happen to be the interval that we were looking at, like the endpoints, 0 and 2 pi. That doesn't always happen on trig functions. It depends on the interval I'm given. It depends on the trig function I'm using. But this one worked that way, and it happened again in the middle at pi. Okay, so far so good? So what I actually found from the perspective of this graph is that my sine of x equals 0, it happens at x equals 0, pi, and 2 pi. So that's a graph perspective. Let's talk from a unit circle perspective in case that's the perspective you're thinking of it instead. Okay, so on a unit circle, the sign values are the y values. And if I want my y values to be 0, that means those are the x-intercepts. So these are the locations, right, on the left side and on the right side of the unit circle where I have sign values of 0. And this is at 0, this is at pi, and then it rotates back around. This would be 2 pi, and it would go to 3 pi, and it would keep going indefinitely as far as we needed it to. Those values that we have that are on our interval, again, are 0, pi, and 2 pi. So you can think about it from a unit circle perspective if that's more helpful. But we do have 3 locations. So those 3 particular values are the ones we're going to test now. This is step 2, right? I test my critical numbers in the original equation. That's that cosine equation I started with. So I need to find g of 0, g of pi, and g of 2 pi. And we also get this almost for free on this one because 2 of those are my endpoints. So when we get to step 3, I don't have to do step 3 because I already did the endpoints because they happen to be critical points as well. So as I'm looking at each of these, I've got 3 cosine of 0. Do you remember what the cosine of 0 is? It's 1. So this is actually equal to 3. And if you want to use your calculator to find it too, that's fine. It's not going to hurt anything. This is 3. What about 3 cosine of pi? Negative 3. And how about 3 cosine of 2 pi? That one's 3 again. So again, because my interval is big enough, again, it kind of shouldn't surprise us. There is the possibility sometimes that we have locations where we have, especially with trig functions, 2 maximums, right? These have the same y value, and they are the largest. So these are both maximum values. So we have a maximum of 3 at x equals 0 and 2 pi. And again, remember, the only reason I didn't have to test the endpoints is because I already tested them by default. Otherwise, I'd still have one more step before I did this. And then my minimum of negative 3 at x equal pi. Or if you're writing them in ordered pair form, you would say we have a maximum at 0, 3, and at 2 pi, 3. And you have a minimum at pi, negative 3. Any questions on those? All right, so we're done for today. 3.1 will be due on Friday on WebAssign, so make sure you have taken a look through and started working on and finishing on that. And I'll have your tests on Friday as well.